In this session, we're going to begin working on the review for Chapter 6. In Problem 1, we have an isosceles triangle, triangle ABC, with line BD perpendicular to the base. Now, we can show that because AB is congruent to BC, and BD is congruent to itself by the reflexive property, we have the hypotenuse of a right triangle congruent to the hypotenuse of a second right triangle, and the corresponding legs are also congruent. Therefore, these two triangles are congruent by hypotenuse leg. This tells us that this is the perpendicular bisector of this triangle. And in fact, any altitude from the vertex of an isosceles triangle that's perpendicular to its base is a perpendicular bisector of that base. Therefore, AD is congruent to DC. So using that concept, we will solve for DC. So 20 equals 7x minus 15. We will add 15, 35 equals 7x, divide by 7, 5 equals x. We take that value and we substitute it in here. We don't really even have to do that, but we're going to do it as a cross check because we want to make sure that this side equals 20. So 7 times 5 minus 15 is 35 minus 15, which is 20. So yes, in fact, DC equals 20. So we didn't have to do all that work. We could have just determined, because this side was congruent to this, that this side would in fact be 20. For problem 2, the theorem that's at work here is the theorem that says if a ray bisects an angle, then every point on that ray is equidistant from the sides of the angle. And we can see that's evident because if we take a look, we have this triangle with a right angle and one angle congruent to the right angle and corresponding angle of the second triangle over here, and we know that this side is congruent to itself. So here we have angle, angle, side, angle, angle, side. So these two triangles are congruent, so therefore PS must be congruent to SR. So again, the theorem that we're working with is the theorem that says any point on the angle bisector of an angle is equidistant from the sides. So since we didn't get any values like we did over here, we're actually going to have to work this one out. So let's go ahead and work out number 2. So we have 6x plus 5 is equal to 9x minus 4, because this side is congruent to that. Let's subtract 6x from both sides. So 5 equals 3x minus 4. Let's add 4. 9 equals 3x. Divide by 3. 3 equals x. Now we're going to take that x value and we can substitute it into either one of these expressions. So since we're looking for RS, let's put it in there. Doesn't really matter. 9 times x value is 3 minus 4. 9 times 3 is 27 minus 4, 23. So we know that RS equals 23. Now on to problem 3. In problem 3, we're dealing with the converse of this theorem. Here we have JH is congruent to JG, meaning that J is equidistant from GF and from FH. So this point is equidistant from the sides, and we know because this is a leg of a right triangle, this is a leg of a right triangle, this is the hypotenuse, which is shared by both of these triangles. So by hypotenuse leg, this triangle is congruent to this, and therefore these two angles must be congruent. So this angle and this angle must be congruent. So if this angle is 47, then this angle must be 47. Therefore JFH has to equal 47 degrees. And so we just write that, and that is problem 3. Now on to problem 4. In problem 4, we are told to find the coordinates of the circumcenter of the triangle with the given vertices. Now, this is not the triangle we're talking about. This triangle is for problem 6. So here we actually have to plot the coordinates of this triangle TUV. So to save time, I've already done that, so let's bring that up. So here's our triangle TUV. T is at -6, -5, U is at 0, -1, and V is at 0, -5. Now, we're looking for the circumcenter. The circumcenter is the point of concurrency of the perpendicular bisectors of the sides of the triangle. Now, we're kind of lucky here because we have a horizontal line and a vertical line. And so the perpendicular line to a horizontal line is a vertical line, and the perpendicular to a vertical line is a horizontal. And they were nice enough to give us a fairly simple set of problems here. This coordinate is -6 and 0, so this is 6 units long, and so the midpoint is going to be right there. And likewise here, this segment is 4 units long, so the midpoint is going to be here. So let us go ahead and create perpendicular bisectors of this segment and this segment. So the perpendicular bisector of TV is the line x equals -3, and the perpendicular bisector of UV is y equals -3. And you can see that those points, those lines, intersect right here at -3, -3. So we'll go ahead and create a point there. And here's our point of concurrency. And we'll call it point A at -3, -3. Now this is the circumcenter, which means that this is the center point around which all the vertices of this triangle are equidistant. So in other words, if I were to draw a circle centered on that point, that circle would go through T, U, and V. So let's go ahead and do that. So we'll go ahead and start here, and we'll draw our circle out to this point, and you can see that that in fact was the circumcenter, and it goes through all these. And now on to problem 5. In problem 5 we have another triangle, X, Y, and Z, and the coordinates are a little bit different, so let's go ahead and bring that up and plot those. Okay, problem 5 is going to be a bit trickier because they only gave us one horizontal line right here. So we know that somewhere on the line x equals 4, we're going to have the point of concurrency of the perpendicular bisectors of these segments. But in order to find it, we're going to have to find the midpoint of one of these two segments. Let's just go ahead with xz. So to find the midpoint is just the average of the endpoints. So let's find the average of the endpoints. We have -2 plus 6 over 2 and 1 plus a -3, which is -3 over 2. That gives us 4 over 2, which is 2, 1 minus 3 is negative 2. Negative 2 divided by 2 is negative 1. So our midpoint is 2, negative 1. So 2, negative 1. So there's our midpoint there. Now, what we're going to have to do is we're going to have to do a bit extra work, because we're going to have to find out where this line, the line x equals 4, and the line perpendicular to xz intersect. So that means we need to find the equation of a line through this point perpendicular to this line. So first thing is we need the slope of xz. So the slope is the difference of the y's, so 1 minus negative 3, that's 1 minus negative 3, divided by negative 2 minus 6. 1 minus negative 3 is 1 plus 3, which is 4. Negative 2 minus 6 is negative 8, which gives us negative 1/2. So the slope of this line is negative 1/2, which means the slope of a line perpendicular to it is going to be the negative reciprocal. So our target slope is 2. Now we can use this point, 2, negative 1, and this slope, and find the equation of the line. So let's give ourselves a little bit of space here. So we can say y minus y1 is negative 1, so that's y plus 1, equals m, which is 2, times x minus x1, which is 2. So solving for y, y plus 1 equals, distribute the 2, 2x minus 4, subtract the, that's a 4, not a y. Y, subtract the 1 equals 2x minus 5. So the equation of the line perpendicular to this line through that point is this equation, y equals 2x minus 5. And so that line is going to be approximately, now we know that the line x equals 4 is going to intersect this. Therefore, the point along this line is going to have an x coordinate of 4, which means it's all we really have to do is plug in a 4 for this x coordinate, and we'll have our target y coordinate. So let us go over here and say y equals 2 times 4 minus 5. Again, the line is x equals 4, so the x coordinate must be 4. The x coordinate must be 4 along this line. So y equals 2 times 4 is 8, minus 5, which is 3. So we know that the coordinate of this point is going to be right about there, and it's going to be 4, 3. And that is going to be our new circumcenter. So let's, just for kicks, let's go ahead and put a line along there. And then let's go ahead and add our circle centered at 4, 3. And there you have it. Now let's move on to problem 6.